When we're studying differential equations, one of our tasks is to find solutions to them, which means we want to find functions that make the equation true. Some equations are what are known as separable. Separable equations are ones where the derivative, it's a first order differential equation, the derivative can be written as a product of a function of x and a function of y. It's separable in the sense that we have these two factors, one which only involves x, the other that only involves y. We're going to talk in this video about how to solve these equations. So our differential equation is first order, first derivative equals some function of x and y. Write it as a product of those two functions, one in x and one in y. And then we treat dy and dx as differentials, hence the name differential equations. So we can treat them as independent variables, well, variables, not independent variables, but variables, multiply both sides by dx, and divide both sides by g of y. So you'll have dy over g of y equals f of x dx. Now we'll integrate both sides, and then we find the antiderivative of each side. You should have a constant of integration, technically on both sides of the equation, but you could subtract one constant from the other one side, and you'll only need one constant of integration. Usually it's put with the dependent or the independent variable x. Now this looks a little intimidating, d of y over g of y. G of y could already be a fraction, and so it's not necessarily something in the denominator, so don't be intimidated by that. Once we've done that, we've found our antiderivative. Sometimes an initial condition is given. What is y of 5, for example? If we know that, then we can substitute that in and figure out what c is equal to. Most of the time, we like to solve our equation for y. Okay? I'm okay, it doesn't really matter when we solve for c. I typically like to solve for c before solving for y. Let's look at our first example. We have x squared dy dx equals e to the y. Okay, what I notice is I've got dy dx. I can multiply both sides by dy. I'll get or dx. I get x squared dy equals e to the y dx. The variables have to match up. I've got dy on the left with an x squared, that doesn't work. And I've got e to the y with the dx, that doesn't work. The dx has to be with the x's. So we're going to multiply or divide both sides by x squared, and let's divide both sides by e to the y at the same time. Now I left a little bit of space because now that we have the variables separated, that's why we call them separable equations, we've got dy with the y's, dx with the x's, we can integrate both sides. Now, in order to find the antiderivative here, we need to rewrite each of these using properties of exponents. This is going to be e to the negative y dy equals the integral of x to the negative 2 dx. And we find antiderivatives. The antiderivative of e to the negative y is negative e to the negative y. The antiderivative of x to the negative 2, the exponent will be 1 larger, so it'll be negative 1, and we'll divide by negative 1, which is the same as multiplying by negative 1. Now, I will say this is the point at which we add our constant, okay? We don't add the constant after we solve for y, so it'll be a plus c. I also should just take a quick note as to why we have this negative here in front of the e to the negative y. That's because the exponent isn't simply y, it's negative y. If I were to find the derivative of the left side and use the chain rule, I'd have e to the negative y times negative 1. And so we use that negative out there to eliminate the negative 1. Okay, so I'm going to rewrite things in a slightly different fashion. The left side, I'm going to make it, let's say, negative 1 over e to the y equals negative 1 over x plus c. Now again, I said we want to solve this for y. I'm going to multiply both sides by negative 1. 1 over e to the y equals 1 over x minus c. Some people might replace that with a new variable like plus k, but we'll just leave it as minus c. If we multiply both sides by e to the y and divide by 1 over x minus c, we get 1 over x minus c in the denominator equals e to the y. And then we can take the natural log of both sides. But before we do this, maybe I'd like to make some sort of algebraic simplification. Let's multiply by x over x here to get rid of the 1 over x in the denominator. That's not necessary, but it just makes our equation look nicer. I'll have x divided by, when you distribute the 1 over x to both of those terms, you'll get 1 minus cx equals e to the y. And now using the natural log of the absolute value of, not the absolute value, but the natural log of x over 1 minus cx will be equal to y. So that's the solution. That is a general solution to this differential equation. For our next example, we have an initial condition, so this is slightly different. Another thing that's slightly different is we're given the derivative in prime notation, r prime, as opposed to Leibniz notation, d something, d something. We're going to make two initial rewrites here. First, r prime I'm going to write as dr dt. And then my goal is to separate the r's and the t's from each other. Well, right now they're huddled underneath that cube root, so let's unhuddle them. Let's use a property of roots. That's the cube root of r multiplied by the cube root of t. This allows us to bring the dt to the right side by multiplying by it. Well, in that case, I'd have the cube root of r with the dt, and I don't want that, so we'll divide both sides by the cube root of r. And then we'll have the cube root of t dt. I'm going to integrate both sides, and at the same time I'll rewrite using my exponents. That's r to the negative 1/3 dr equals the integral of t to the positive 1/3 dt. Using our antiderivative formulas, the new exponent on the left side will be the 2/3 power when I add 1 to that, and so I have to multiply by 3/2 so that when I take the derivative I don't have a coefficient other than 1. And on the right side we'll have t to the 4/3, which means we need to multiply by 3/4 out front. Again, do not solve for r now, put your constant in. You can figure out what the constant is now, or you can solve for r now. I prefer to find the constant first. So I know that from the initial condition up here that if t is equal to 1, r will be 8. So we'll substitute these guys in. So I have 3/2 of 8 to the 2/3 equals 3/4 of 1 to the 4/3 plus c. This is not going to be terribly pretty. That's a 1, not an 11. 8 to the 2/3 is 4. The cube root squared. And then 1 to any power is just 1, so that's going to be 3/4 plus c. The left side will be 4 divided by 2 is 2, times 3 is 6, and 6 minus 3/4 will be 21/4. That's what c is equal to. So we like to put all this back together. Let's erase that so we have some room. And we like to put it all back together. So I have 3/2 r to the 2/3 equals 3/4 t to the 4/3 plus 21/4. Now we want to solve this for r. I want to get r all by its lonesome. Well, first of all, we have to get rid of the 3/2, so I'm going to multiply both sides by 2/3. We'll get r to the 2/3 equals, that if I distribute, we'll end up with 1/2 t to the 4/3 . 4 to the 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 4 And then what would that be? Plus 7/2. And now comes the fun part. How are we going to do this, get rid of the exponent here? Well, there are lots of ways we could go about doing it. It's not always natural for students to see this. So one thing you could do is you could say, oh, well, let's, well, the third power, that would be like the cube root of r squared, would it not? I'm just thinking here. And so in order to get rid of that, I would have to cube things. So I'd have to have something to the third power. And then I would end up with just r squared. And to get rid of that, I'd have to take the square root of everything. And if you rewrite that as an exponent, that is something to the 3/2 power. Okay, so the 3/2 power is important here. Let's go back and deal with this. I would love to get rid of that exponent. The way to get rid of an exponent is to use exponent rules. And the 3/2 comes into play. So r to the 2/3, if we raise that to the 3/2 power, we would have to multiply those exponents, which would give us 1, which is wonderful. But if I do that to the left side, I have to do it to the right side as well. And so we end up with a solution of r equals 1/2 t to the 4/3 plus 7/2 to the 3/2. Okay, our next example looks very intimidating. Let's just highlight it so we can see what we're dealing with here. That is our differential equation, and we are given an initial condition here. So the first thing we want to do is we want to isolate the derivative. And this one's a little bit misleading. The x is in the numerator, so we have dx as opposed to something dx. It's a little bit unusual. But I'd have dx dt equals 1 minus 2t minus 2tx minus x. I'm supposed to separate this. I want to get some expression in x multiplied by some expression in t. And I've got lots of subtraction. That doesn't seem to make sense to me to be able to do that. And I did make a mistake here. When I added x to both sides, that should be plus x. Okay, so I start looking for other clues. Well, here's a clue to me. I have a minus 2t and a minus 2tx. So I'm going to group those guys together and literally do exactly that. I'm going to group them. I'm going to put the 1 plus x first. And then I'm going to put the minus 2t minus 2tx together. And then I have the 2t in common with both of those. So I'll factor it out. But since both are negative, let's factor that out as well. So dx dt is 1 plus x. I'm sorry. Well, we can leave it like that. And then minus 2t, I've factored that out. From the second term, because I factored out the negative, it'll be plus x. And then we have 4 terms here. We factored 2t from 2 terms, so I still need a term in the middle. You might want to put a little multiplied by 1 there. That's 1 plus x. Okay, so now I see a common theme of 1 plus x in these two guys. And so I'm going to factor that out. And again, we might want to go back in here and put a multiply by 1 just so I can see it. If I factor out the 1 plus x, we get 1 plus x multiplied by 1 minus 2t. And now I have what I needed. I needed some expression in x multiplied by some expression in t. Oops, and I wrote that thing wrong here. That should say dt. And so I'm going to multiply both sides by dt and divide by 1 plus x. Dx over 1 plus x equals 1 minus 2t dt. And we're ready to integrate. Left side, well, it's almost like 1 over x. That would be the natural log of the absolute value of x. But it's 1 over 1 plus x. So would it be the natural log of the absolute value of 1 plus x? Well, let's check it with the chain rule. the chain rule would say it would be 1 over 1 plus x times the derivative of 1 plus x, which is 1. So yes, that works. On the right side, on the other hand, we have t minus t squared. Again, throw your constant in now. Okay. We want to find out what that constant is. So we'll put 2 in for t and 0 in for x. Okay, so we'll have on the left side, we'll have the natural log of the absolute value of 1 plus 0 equals x is, or t is 2, isn't it? 2 minus 2 squared plus c. And the natural log of 1 equals 0. So the left side is 0, the right side is negative 2. If we add 2 to both sides, we get 2 equals c. So I end up with the equation natural log of the absolute value of 1 plus x equals, I don't know why, but I want to put the 2 first. 2 plus t minus t squared. Okay, so we're going to learn one important lesson here with all this. I need to solve this for x now because it's dx dt. T is the independent variable, x is what we want to solve for. In order to rewrite it where we don't have a natural log, we're going to use the exponential function, so it'll be e to the 2 plus t minus t squared. On the left side, we have the absolute value of 1 plus x. So here's the important lesson. Can we get rid of the absolute values? Yes, we can. The reason we can is because we were given some information here about x at some particular value. When I substituted 0 in for x down here, the argument of the natural logarithm was a positive number. So we're going to make the assumption that anytime we plug an x value in, it will be positive. So we really don't need those absolute values. And we can write our final answer as x equals e to the 2 plus t minus t squared minus 1. There is our final answer. Oh, it just keeps getting good, doesn't it? Okay, so I have this thing here. dy dx is all that stuff. Okay, we've gotten the practice of this, so we're going to bring the y's to one side, bring the x's to the other, the dx to the other side, and at the same time I'm going to write things so we're ready to integrate. So I would be dividing by y squared. We'll have y to the negative 2 dy. That's from bringing this y squared, dividing by it. When we bring it back up, it's up to the numerator. And then that's equal to x dx over the square root of x squared plus 3. Okay, how did we get that? We multiplied both sides by dx. Okay, and now we're integrating. The right side we might recognize is going to require a method of integration. This one, I often will look and say, hey, derivative of x squared plus 3 is 2x, and there's an x lurking in the numerator. Oh, so letting u be x squared plus 3 seems like a good substitution. So on the left side, we'll end up with negative y to the negative 1. On the right side, we'll remain with, let's see, oh, well, I didn't finish my substitution. du is 2x dx. So I'll have 1/2 du equals x dx. So the numerator becomes 1/2, which I'll slap out front. And then the dx was 1/2 du. And the denominator was the square root of what we let u be equal to. Okay, so this is u, and we'll bring that up as u to the negative 1/2 du. So negative y to the negative 1 equals 1/2. When we add 1 to the exponent, we'll end up with a 1/2. We need to multiply by the reciprocal of 1/2 out front, which is a 2. Ooh, that's kind of nice. And then we add our constant. So the 2 and the 1/2 will reduce. On the left side, I'm going to rewrite that as negative 1 over y equals u to the 1/2. Well, u was the square root This will be the square root of x squared plus 3 plus a constant. Okay, so we know that y of 1 is equal to 4. Y of 1 is 4. So when x is 1, y is 4, we'll get negative 1/4. So we have negative 1/4 equals 2 plus c. Subtract 2, we end up with negative 9/4 equals c. When we put this all back together, let's see what we get. I will have negative 1 over y equals the square root of x squared plus 3 minus 9/4. Multiply both sides by negative 1. 1 over y will equal 9/4 minus the square root of x squared plus 3. Multiplying the right side by negative 1 reverses the difference. And then if we multiply both sides by y and divide by both sides by the right-hand side, we end up with 1 over 9/4 minus the square root of x squared plus 3 is equal to y. If you want to, you can multiply numerator and denominator by 4 to eliminate the fraction within a fraction. And so we would get 4 over 9 minus 4 radical x squared plus 3. All right, for this next example, we'll learn another important lesson that we have to pay attention to our initial conditions when making some assumptions about our functions. This is not a terribly difficult one to do. We multiply both sides by y cubed, multiply both sides by dx, and we have a very nice and symmetric looking thing, y cubed dy equals the integral of x cubed dx. Ooh, this is great because I get to use the same formula twice. 1/4 y to the 4th equals 1/4 x to the 4th. This again is important. Put your plus c now. Okay, so y of 0 is equal to negative 2, which means that if x is 0, y is negative 2. Okay, well, let's put this all in. If x is 0, we'll get 0 on the right side plus c equals 1/4 of negative 2 to the 4th. That's 16 divided by 4 is 4. That's what c is going to equal. So here's where we're going to have to be very careful when it comes time to solve. We get 1/4 y to the 4th equals 1/4 x to the 4th plus 4, because that's what we found c to be equal to. Multiply both sides by 4, we get y to the 4th equals x to the 4th plus 16. And here's where we've got to be careful. I'm going to take the 4th root. Now, there are 2 4th roots that we have to worry about. There is what we call the principal 4th root, which is the positive, and then there's the opposite of that. Which do we want? The mystery abounds. So we will get the 4th root of x to the 4th plus 16. Now, this is where the initial conditions come into play. Notice that y of 0 is negative 2. If we plug 0 in for x, we're going to get the 4th root of 16, which we always take the positive, the principal 4th root, which will be positive 2. So I mentioned earlier, just a minute ago, that we have to decide whether we want the positive one or the negative one. Because y is negative up here, we need to choose the opposite of the principal 4th root. Okay, now please, whatever you do, do not say this is equal to x plus 2, the 4th root, or even, okay, negative x plus 2. The 4th root does not distribute like that. For our last example, we have an application problem where we have a tank of salt water whose concentration is changing because we're adding salt water in that's a different concentration while draining the tank at the same time. Our tank has 500 liters of salt water, which contains a total of 12 kilograms of dissolved salt. We're given the concentration of the salt water that's entering, 0.02 kilograms per liter, and the rate at which it's entering. So I hear rate, I think differential equation, derivative. Somehow we instantly thoroughly mix this, and the water drains from the tank at the same rate of 15 liters per minute. Now, in these kinds of problems, you want to very carefully choose what you let your variable represent. We are asked how much salt is in the tank after t minutes and then after 2 hours. Well, since we're asked that, we'll go ahead and we'll say that y is the amount of salt. This is measured in kilograms after t minutes. Okay, so as I said, everything seems to be given to us in terms of a rate, and so we're going to look at dy dt, which is the rate. Dy dt. The concentration is changing because of two things. One, we have brine solution coming in, and two, we have it going out. And so this will be the rate in minus the rate out. Okay, so we'll go ahead and we'll replace those here in a moment with what they're equal to. The rate in is a constant, right? The rate in. Now wait, this is the rate at which the salt is changing. Okay, so we have two components to this. We have 15 liters of the salt solution coming in. Each of those liters is 0.02 kilograms per liter. So my rate in is going to be the 0.02 kilograms per liter multiplied by the 15 liters per minute. And we see that the units of liters will cancel, and we end up with kilograms per minute, and this turns out to be 0.3 kilograms per minute. So we'll replace that over here. We get 0.3, and we're going to subtract the rate out. For the rate out, we're going to do something similar. It's a little bit more complex, though. We are going to do very much the same thing here. The rate out will be a concentration, which is in kilograms per liter, multiplied by the rate at which it's leaving, the number of liters per minute. Well, that 15 does not change. It's the kilograms per liter that will change. Now think about the 0.02. It is a concentration. It's the number of kilograms per liter. And so if we think about this tank, it holds 800 liters. Okay, so the denominator measures the number of liters, well, the numerator measures the number of kilograms. Of course, this is changing, and way up here, a little while ago, we said y is the amount of salt after t minutes. So that's the number of kilograms of salt after t minutes, and so up here we'll put y. When we simplify this, the 15 and the 800 have a common factor of 5, so we end up with 3 divided by 160, and that's kilograms per minute. So we'll replace the rate out with that. And that should read actually 3y over 160. I left off the y there momentarily. And so we have 0.3 minus 3y over 160. Okay? I'm going to do a little bit of a manipulation here. I'm going to multiply both sides by 160 to get rid of the fractions. And if I do that, I'll end up with 160 dy dt. Multiplying 0.3 by 160 gives us 48 minus 3y. I'm going to multiply both sides by dt and divide both sides by the 48 minus 3y. So we end up with 160 dy divided by 48 minus 3y equals, well, just dt. We multiplied by dt, we divided by that other stuff. And so now we're ready to find the antiderivative. We're going to integrate this. The left side, I'm going to write the 160. I'm going to leave a little space because I've got to make an adjustment here. But I have something that looks like 1 over y, almost. It's 48 minus 3y. So it's going to look like the natural log of that business. We've got the natural log of the absolute value of 48 minus 3y. And on the right side, we would have t plus a constant. Okay, so I left the little space there because if I take the derivative of the natural log of 48 minus 3y, the chain rule would ask me to multiply by a factor of -3 for the derivative of the inside, which will need a negative 1/3 out front there. Okay. At this point, I'm going to go ahead and solve for c. I need some extra piece of information here, though. We'll go up here and we'll notice that at the beginning, there were 12 kilograms of salt in the tank. So at the beginning, that means t equals 0, y will be equal to 12. We'll go ahead and substitute in those values. I'll make this negative 160 over 3 times the natural log. When we substitute y in, or 12 in for y, we'll have 3 times 12, which will be 36. 48 minus 36 is 12, so it's the natural log of 12. T is equal to 0, so that's going to be my constant of integration. If we rewrite all this together, we end up with negative 160 over 3 times the natural log of the absolute value. Now I'm actually going to take away the absolute value. Let me explain why. We'll have 48 minus 3y. This is going to be equal to t plus this awful thing, negative 160 over 3 natural log of 12. The reason I can remove the absolute values is because that when we substituted 12 in for y, we ended up taking the natural log of a positive number, and so we may assume that it's always positive. We'll now solve this for y. It's going to look a little messy, but it gets a little prettier. If we multiply both sides by negative 3 over 160, we end up with the natural log of 48 minus 3y equals negative 3 over 160 plus the natural log of 12. If we exponentiate both sides, take e to both sides, we end up with 48 minus 3y equals e to all this business. I'm going to write the natural log of 12 first, and I lost my t. Minus 3t minus 3t divided by 160. And I'm going to use a property of exponents here next and subtract 48 from both sides. So I have negative 3y equals, this will be the e to the natural log of 12 times e to the negative 3t over 160 minus 48. And now I'm going to divide both sides by negative 3 and reverse things a little bit. At the same time, I'm going to acknowledge that e to the natural log of 12 equals 12. And we end up with y equals negative 48 divided by negative 3 is positive 16. The 12 that's represented above by e to the natural log of 12, that 12 divided by negative 3 will become minus 4. And then e to the negative 3t divided by 160. So this is the formula. It took us a long time to get here, but this is the formula that we were looking for. Okay, we want to make sure, or we want to go ahead and find out what's happening after 2 hours. So we'll substitute 120 in for t. Remember that t is measured in minutes. So we end up with y equals 16 minus 4e to the negative 3 times 120 divided by 160, which is equal to 15.578 kilograms approximately. Okay, so for our final little bit here, we want to know what happens to the amount of salt in the tank in the long run. Remember, our function is y equals this 16 minus 4 e to the negative 3t over 160. And so what we're really looking for is we're looking for the limit as t approaches infinity of this business. If we let t go to infinity, the exponent is going to be a very, very, very large negative number. E to a very, very large negative number is like 1 over e to a very large positive number. And e to a large positive number is ginormous. And so this is almost 0. So this turns out to be 16 minus 4 times 0, or it approaches 16 kilograms. Now this actually makes sense. And the reason this makes sense is because if you imagine that the water in the tank to begin with is blue, and the water that we're adding is red, over time it'll turn more and more purple, and then it'll change to red. It'll become all red. And the red then has a concentration of 0.2 kilograms per liter. If you multiply that by 800, you get 16 as well, which makes sense because the original solution has been replaced by what we're adding to it.